Moving beyond the basics of software-defined radio, where we transition from radio as a hardware box to radio as an app, requires looking at the architectural bottlenecks and the advanced signal processing strategies that make modern high-performance systems possible. In 2026, the field is dominated by the move toward all digital front-ends and the integration of AI for real-time spectrum management. Traditional SDRs like the RTL SDR, which I have shown, often uses a superheterodyne or direct conversion, that is zero intermediate frequency architecture. These rely on analog mixers to move signals down to a frequency the computer can handle. The current gold standard for high-end SDRs like high-end flex radios is direct RF sampling. The analog to digital converter or ADC is placed as close to the antenna as possible. There is no analog down conversion. The challenge is to sample a 3 GHz signal directly, you need an ADC sampling at over 6 gigasamples per second to satisfy the Nyquist theorem. Simply put, Nyquist frequency is half the sampling rate. The benefit is that it eliminates analog artifacts like IQ imbalance, DC offset, and phase noise introduced by local oscillators. Direct conversion receivers contain a local oscillator which generates both a sine wave at carrier frequency and a copy phase delayed by 90 degrees. These are individually mixed with the RF signal, producing what are known respectively as the in-phase and quadrature signals, labeled I and Q. In practice, actual phase difference may not be exactly 90 degrees and the gain may not be equal in these two signals, causing IQ imbalance. DC offset is the value introduced by the DC bias so that the mean value of a sine wave becomes non-zero. Phase noise describes random short-term fluctuations in the phase or frequency of a signal from an oscillator. A common beyond basics hurdle is understanding where the math happens. General purpose processors, example the one in your laptop CPU, are great for complex protocols like decoding a P25 digital radio trunk, but it struggles with massive raw data rates. Project 25 or P25 is a suite of standards for interoperable land mobile radio system designed primarily for public safety users. Then what is this FPGA or Field Programmable Gate Arrays? These are the secret sauce of high performance SDR. Because they process data in parallel, they can handle the massive fire hose of bits from a direct sampling ADC in real time. ADC is analog to digital converter. The workflow, usually an FPGA performs digital down conversion, filtering and thinning out the data so that a standard USB or Ethernet cable can actually carry the result to your PC. You may have heard several ham radio operators discussing regarding all these aspects, as many have switched to modern digital down conversion radios. We are moving from SDR to cognitive radio. In a cognitive system, the radio doesn't just sit on one frequency. It perceives the environment, that is dynamic spectrum access. The radio senses white spaces or unused frequencies and automatically hops into them to avoid interference. Neural demodulators. Instead of writing a mathematical formula to decode a signal, researchers now use convolutional neural networks. They can decode signals even in extreme noise or low signal-to-noise ratio situations where traditional math-based decoders fail. By synchronizing the clocks of multiple SDRs, you can achieve spatial multiplexing, the passive radar. You can use two SDRs to quote-unquote see objects without transmitting. You know that conventional radar transmits and receives the reflected signals. One listens to a known source like a TV tower and the other listens for the reflection of an airplane. By comparing the phase difference, you can calculate the plane's position. Beamforming. By precisely shifting the phase of a signal across multiple antennas, you can steer the radio beam electronically, focusing energy on a specific target without moving the hardware. Usually we rotate the antenna using antenna rotators for satellite access and things like that. But this is electronic steering of the beam using phased arrays. There are phased array antennas being used by AM radio operators even now. Here is a comparison between entry-level SDRs like the RTL SDR which I have and high-performance SDR like Blade RF. Analog to digital conversion or ADC resolution for entry-level SDR is 8-bit with limited dynamic range, while it is 14-bit or 16-bit for higher ends. They can hear weak signals near loud noises. The sample rate is around 2.4 megasamples per second, so it takes a small slice of the spectrum. It is up to 1 plus gigasamples per second and can see the whole band for advanced ones. Clock stability is 1 to 2 parts per million and it can drift as it gets hot. It is less than 0.5 parts per billion, that is the oven controlled or GPS disciplined ones in advanced radios. The entry level is receive only like my RTL SDR, while research grade ones are full duplex. That means they can transmit and receive simultaneously. We have full duplex analog radios like the IC2730A radio which I have, which can transmit and receive for satellite operations. Many beginners think more bandwidth is better. However, in beyond the basics SDR, dynamic range or bit depth is often more important. An 8-bit SDR will be quote-unquote blinded by a nearby FM tower, whereas a 16-bit SDR can quote-unquote see a tiny signal right next to that tower because it has 2 to the power of 16 levels of resolution instead of 2 to the power of 8 resolution.